It's finally ready. Sorry for the delay. So hi, everyone. Thank you, Rocco, for the very nice introduction. And more globally, thanks to all the organizers for this very nice workshop. And last big thank you, Blake, for introducing so many notions I wanted to talk about, so it's going to be way easier for me. I may need a chalk at some point, so I prefer taking it beforehand. So today, I'm going to talk about scaling law for ResNets, the specific example of ResNets. So the overall purpose of my presentation is to give some practical hints on how to choose the scalings in the ResNets, especially if you want to achieve feature learning, and to give some mathematical tools, not all of them, but at least some of them, that are useful to compute quantitative rigorous limits in ResNets from a mathematical point of view. First thing I have to say is that most of the material I'm going to present is borrowed from Linnaeus Shisa. So I'd like to say that Linnaeus Shisa is not responsible for all the mistakes that I will do today, but for all the content that may be interesting, he's responsible for. So let me start. If it works. Yes, it works. So I'm going to show exactly the same picture as Blake, which is this famous study by Kaplan and co-authors that just motivates something I think that all of you are convinced today, which is the fact that it's useful to have bigger architectures if you want to achieve better performance. An interesting thing on these figures is the fact that if you have a given architecture, so on this plot here, you can see the test loss on the left-hand side for a given architecture that is scaled in several ways. Always the same, but that is scaled, scaled, and scaled, and then tested on the same task. And the main point here is the fact that if you fix the architecture and you just compute a lot, you train a lot, you're going to have a threshold that you cannot beat unless you scale up your model. So it's just the genuine idea that if you want to achieve better performance, you have to choose a bigger model. There are several ways of having a bigger model, which is already something that Blake said a lot, that Mufan said a lot, which is you can have more data, you can have longer training time, or you can use bigger models. And today I will talk about scaling, so the question of bigger models, how to choose the right scalings so that your model is efficient. So the goal is to choose the hyperparameters, and the hyperparameters that we'll be interested in today are the scalings. So just to give a global picture that would be important in order not being lost in the remaining of my talk, which is this one. This scheme is just a schematic representation of what happens in a residual neural networks, or more generally in neural networks. You start with some data here. You embed here, so you have an embedding dimension D. Then you have the whole architecture here with some width M and some depth L. And in the end, after going through the whole network, you just unembed it and you get the output. So the point of this slide that I'm going to schematically rewrite here is just to fix the notations that will be useful throughout my presentation. So D is the embedding dimension. M is the width of a network. And L is the depth. So exactly like in Blake's presentation. Since a lot has already been said on this, I won't spend a lot of time on motivations, but still there is a very remarkable fact that I want to further emphasize. So once again, I take your picture, which is a direct application of well choosing the scaling, which is the zero-shot hyperparameter transfer that was initially introduced by Greg Young and co-authors in 22. So in the fourth paper of the tensor program series, Greg Young introduced a very interesting idea of maximal update and the mu-p scaling, which was well defined for very wide networks. And then the question was raised, I mean, how do you adapt this idea for very deep network? And there are several ways of doing so. There was the so-called deft mu-p, and then the complete p scaling, which was introduced by this paper of ProbAI and co-authors and Day and co-authors, including some of you that are already present in this room. And just the nice thing to see on this picture is the thing that Blake already mentioned, which is the fact that actually, if you have well chosen your hyperparameters, then you can do hyperparameter transfer, so that you can choose the relevant parameters, like, the learning rate that you can see here, on a small architecture, and then directly extrapolate it. It's the zero-shot transfer to wider architectures. But since it has already been said, I won't spend a lot of time on it. It was just to give some motivation of why while choosing the scaling. Now, I have to do a bunch of citations. I mean, I apologize for all the ones I won't be able to cite today because there are so many of them that have already worked on these questions. I would just like to mention several scaling that are relevant in the literature. So the first disclaimer is that throughout all my presentation, I will only consider one single regime, which is the regime where the embedding dimension is very small compared to the product of the depth times the width. But in particular, there is still one regime that is relevant and included in this scaling, which is the proportional regime. So in particular, that allows for D proportional to M and L very big. And this regime is particularly interesting to keep in mind because it's a regime that is commonly used in practice. Here I try to give you some figures where you can see that indeed in practical architecture that are particularly relevant. For instance, I took one which was a benchmark for a long time, which is the Llama 3.1 architecture. Taking D proportional to M seems something reasonable, but still the assumption that the product L times M is way bigger than D is something that in practice seems to be met. So it's a reasonable assumption. And this is the main motivation for keeping this scaling. However, throughout my presentation, I will try to decompose the mathematical steps that allow us to study large networks with this kind of scaling. So the plan of my presentation will be the following one. First, I will focus on the case of two-layer perceptron. So two-layer perceptron, with my notations, corresponds to L equals 1 or 2, depending on how you count the number of layers. So it's not 1/2. In the first part of my presentation, I will try to explain the first important thing that I want to give in this talk today, which is how to choose the scaling and how you can mathematically implement the idea of feature learning and complete feature learning. Then I will move to the M goes to infinity limits of 2 LPs. And afterwards, in the second part of my talk, which is, I think, the most important today, I will try to explain, after doing M to infinity, how you do D goes to infinity. And for this very specific case of 2 LPs, this will be necessary, because if I want to meet this criterion of D smaller than Ln, since L equals 2, I have to do the M goes to infinity first. So this part is not the one which is the most important in practice, but at least this is the one that I will use to introduce the theoretical tools that I need in order to do the complete asymptotics. Then I will talk about deep ResNets, and the ultimate purpose of my presentation will be to consider joint scalings where this holds, but everything goes to infinity simultaneously, just to give you a flavor of what will be the plan of the presentation. Another disclaimer, I know that I have only 1 hour right now, so the tutorial won't finish after 1 hour, I know it. I will slightly continue it in the afternoon, roughly for half an hour, I guess. And in the last hour of this afternoon, I will move directly to the joint limit regime. So the purpose of this tutorial is mainly to focus on 2 LPs to give the mathematical tools that will be needed to understand the joint asymptotics that I will present this afternoon. So it's a lot of introduction. Sorry, yes?
So based on your tables of numbers, is your feeling that the correct regime is D proportional to L proportional to M? Or
D proportional to L.
like is everything growing linearly?
Everything is wrong.
Sorry, like in the shapes of the models as you're making them.
Yes.
Is it
So this one.
right? So you sorry, the tables of just empirics like in Llama and other models.
Ah, yeah. Excuse me. Yes.
Yeah. Is your intuition that like the right regime is like L is proportional to D is proportional to M as you go to the bigger and bigger?
Actually, to be fairly honest, as a mathematician, I must say that the figures are still a bit low, so that you can really say that this is the right regime.
I don't know either.
But still, I use it as a motivation to justify why this scaling is useful. And I think this one is relevant because some of the numerical experiments that we can perform in this regime and that I will show this afternoon are consistent to what can be observed in this kind of architecture. But I'm not at the level of claiming that this is the ideal scaling for sure. Is it okay?
Oh, yeah.
Great.
No, I was just wondering if you have to...
Okay, so as announced, I start with what happens on a two-layer perceptron in the large width limit. So first, designing scaling, and then explaining how to send M to infinity. So this is a two-layer perceptron. So maybe I won't go too slowly on this. So you just take as an input the X here. You perform some linear operation of it using a weight vector UI. Then you apply a nonlinearity. And to make things simple, I took the output to be one-dimensional, so that the VI that you have here are just scalar, real numbers. So the set of parameters here is this theta that gathers all the vectors UI, whose dimension is the same as the input, as this is a scalar product, and the scalar weights VI. Then you give yourself a training set, as it is customary in learning, and this training set is a function of the theta parameter. And you have some data points, and I consider label for simplicity, so that you have a loss function that measures how far is the output of the neural networks from the label yi that should be targeted. And then the loss is the weighted sum of all this. Another disclaimer, throughout my presentation today, I will only take a number of data that is finite. So this is a simplification that cannot account for all the learning properties of neural networks. But still, my purpose today is to study the shapes and the architectures. So the question of data is totally out of scope of what I'm going to present today. This is why also most of the time I would just take an even simpler model, as Mu found yesterday, by saying that n equals 1. Then, once you have the parameters, the loss, you perform a usual gradient descent dynamics. So at this stage, you have already several questions that do arise. How do you initialize your gradient descent dynamics? And what are the learning rates? So I took a usual standard gradient descent with learning rates eta u for the u parameter and eta v for the v. So already at this stage, we have 4 parameters to choose and to scale in the right way so that even this small neural network, this two-layer perceptron, behaves well. And the first part of my talk will be to explain what is the phase diagram for this and how you can get intuition on it by simple mathematical computations. First, I must emphasize the first choice that I made in the parameterization of my network, which are the 1 over m here and the m here. Actually, if you take the gradient of f with respect to one of the parameters, you will see the 1 over m here appearing. So this is why there is an m here. But just for you to know, this convention is totally arbitrary. I could have written exactly the same stuff by moving this 1 over m and moving this m, and then the choice of the parameters will change. But the criteria are robust with respect to this. So this is just a simple choice. Now let me explain the criteria that I'm going to use to explain how I choose my parameters. So how to scale all the criteria. So to give a bit of vocabulary, the first important thing to introduce are the pre-activations. These pre-activations are exactly the dot product that were appearing here in my function, so at the top. Then, after having the pre-activation, I apply the nonlinearity and I get the activation, which in a neural network are commonly referred to as the features. So the features are the activations. And the first criterion that I'm going to use is the feature diversity at initialization. Feature diversity at initialization roughly says that when I send m to infinity, I want the pre-activations to stay over the 1. Because if it's not the case, if my pre-activations are 0 as m goes to infinity, or if it explodes, I cannot do anything. And if they are 0, I mean, I am not using the whole feature diversity of initialization. So I'm losing something about my initialization. I'm not exploiting the whole potential of my initialization. This is why this first criterion appears. And this criterion tells me, basically, when I do this computation, so this is a random variable. At initialization, x is deterministic. and I say that the initialization uj here are Gaussians to make things simple. So when I do the computation, I can directly see that the variance here is just the standard deviation of each of the u times the square norm of x, because I had this convention of normalizing the sum this way. So this is why this first simple criterion tells you that sigma u has to be chosen of the order of 1 over the magnitude of x. And here in this first model, the only thing that I send to infinity is the width of the network. This is the reason why I can roughly say that I take sigma u of order 1, because this dimension is fixed. First criterion. Second criterion, which is an important one, maybe it should be the first, it's a matter of convention. I don't want thing to explode as m is going to infinity. This is why, at initialization, I'm going to compute the variance of the output. So at initialization, since everything is Gaussian and independent, the computation of the variance is quite simple. It's just 1 over m squared because I take the variance, and it's a sum of independent terms. I have m terms, so m divided by m squared giving 1 over m. And I have just the standard deviation of each v at initialization that appears. So the criterion of non-explosion at initializations just tells me that sigma v has to be a big O of square root of m. But this non-explosion criterion is not exactly the same as feature diversity, because feature diversity was telling me that I want something to stay over the 1. The second criterion is just saying that I want things to stay bounded, no explosion. This is why this criterion by itself gives some restriction on sigma v, but it is not as precise as the first one that told me that sigma u has to be over the 1, because there is still a huge degree of liberty instead of this, within this. Because you can take sigma v being over the 1, being over the square root of m, you have many possibilities. So this will be 1 degree of liberty that will stay in the end when I will sketch the phase diagram of the whole 2MNP. Then, next criteria. So the next criteria are related to feature learning, the famous thing we are talking about for now a few talks. So to better understand what feature learning means in this setting, I'm going to do a simple computation at initializations to see how the first updates of the weights work through the training. So here I just rewrote the evolution equation of the weights v and u with this m convention that I had already adopted. So the gradient descent algorithm is always the same. I have my learning rates, eta v and eta u, but I still have to scale the gradient of the loss. And if I compute the gradient of the loss, I have this quantity g that appears, which is the gradient of the loss with respect to its second argument. And then by the chain rule, I have other quantities that pop out. Here, the activation rho, the derivation of the activation, and the weight themselves. So the equation for v is slightly simpler than the one for u, because v was in front of the activation, whereas u was inside it. Then, from these simple equations, I can compute the evolution of the preactivation. The preactivation was just a scalar product, so I just differentiate the scalar product. I get this quantity. From this, I can compute the evolution of the output itself in time. So even though my model was a discrete gradient descent, for the sake of simplicity here, I assume it to be a continuous gradient descent. So what I call ft here is just f of theta t. It's just a simpler notation. So if I compute the evolution of this quantity, I just have to use the chain rule once again. First term, I had v in front of the activation, so this first term is simpler. Second term, I had u within the activation. So I use the formula for differentiating the preactivation. I get this. Then I compute the loss. And the loss, once again, is computed a long time by the chain rule. I differentiate what was inside the loss, so the output of the neural net. And then, by the chain rule, I have this GT that pops out. In the end, I get this expression. And this is the expression whose magnitude I want to compute. So I assume that I am close to initializations, since I have initialized with some random variables that are independent from each other. It's quite simple to do these computations, because the terms in this sum here are independent from one another. So I have a sum of m term rescaled by m. So here I know that the order of magnitude of this is eta v. Second sum, here I have m term divided by m, same thing. I have eta u coming from here. And then I have to look at the order of magnitude of this quantity. This is where I need to look exactly of what is the VG that comes here, and to look at how VG is evolving in time. I just do a short time approximation using the equation that is here for VG. And this is how I get this second term. So this means that on a small time, when I do the linearization of a gradient flow close to initializations with respect to time, I can see that the first term is of order eta v, and the second term has this order of magnitude. So now that I have this short computation at hand, I can think about my third criterion for scaling my 2LP. Yes?
Can you briefly explain where the t-squared is from?
Where the t-square comes.
You have t-squared multiplied by eta v squared.
Yeah, I have a t-square here because I have said that VGT is VG0 plus t something. And since I square VG, I have a t-square coming around. This is how it comes. And now I get to the third criterion. The third criterion is a balanced loss decay. I want that at each step of a gradient descent, the loss decay roughly stays of order 1. Because if it's not the case, if it's slower than this, then I'm losing some power of the gradient descent as m goes to infinity. So my third criterion is I want the loss decay to be balanced, to stay of order 1, even though I'm sending all the parameters to infinity. If I want the loss decay to stay of order 1, looking at the two terms that were here, I can see that both of these terms have to be of order 1. And this is how I get the conclusion of this first criterion. I want the eta v learning rate to stay of order 1, and I want the second term in the sum to stem of order 1, meaning that eta u is the minimum of 1 and 1 over sigma square v. Because this sigma v square is not a quantity that I have already fixed, I only said at the beginning of my presentation, so using the second criterion, that sigma v has to be a big O of square root of n, but it's not fixed for now. So I still have a degree of freedom in the choice of a sigma v, and this is why here I have to keep 1 over sigma v square. And then I move to the most important one, the fourth criterion, the feature learning criterion, which I should even call complete feature learning criterion. This criterion means that I want that locally the evolution of a preactivation stays of order 1. Because there are several ways of saying that the loss decay has a is balanced. Because it would be possible that the loss decay itself is of order 1, but for each parameter, the evolution is negligible at its own scale, even though because you have a lot of parameters and you sum them, in the end, the loss decay is balanced. The complete feature learning criterion is roughly saying that you want the evolution of each parameter to stay of order 1, the evolution of each parameter to have the same order of magnitude of the parameter itself. So this could be also called a maximum local update criterion. Because the balanced loss decay is a global decay criterion, whereas the feature learning, the complete feature learning criterion says you that you want the decay to be balanced also at a local scale, at the scale of each parameter. This is why sometimes I will say complete feature learning, sometimes I will say maximum local update criterion. But both these things are the same thing, and the complete feature learning terminology was introduced in this paper by Day and Coffers that Blake already mentioned for deep architectures. So when I come here, I can see what feature learning, by looking at the evolution of a preactivation, I can see that at time 1, the order of magnitude of the evolution of a preactivation is 1 over square root of v if square root of v is bigger than 1, and 1 if sigma v is smaller than 1, which is exactly computed using this expression here, because you can see that the evolution of the preactivation here, you have eta u popping away, you have this criterion for eta u, so this is how you deduce this. So if you want complete feature learning, if you want the evolution of a preactivation to stay over the 1 as the width goes to infinity, then you have to choose sigma v smaller than 1. And this is how you can identify with a simple mathematical criterion this complete feature learning regime. So once I have these 4 criteria, I can put them in a nutshell and obtain the global phase diagram for 2 LPs, which is the following one. So here I have written stuff with respect to the rescale output scale sigma v divided by m. Why sigma v divided by m? Because it refers to what I showed at the very beginning of my presentation. I said that I had 1 over m, a sum of m terms, but in the end the effective scale was sigma v divided by m, because the m that I put in front of my sum at the very beginning was arbitrary. So this is why it's quite natural to parameterize this diagram by sigma v divided by m. Then, the first regime of this diagram is the last one. I said that taking sigma v of smaller than square root of m was a criterion of non-explosion. It was my second criterion. This is why above this threshold, you just have explosion, so you cannot say anything about it. Then I said that the complete feature learning happens when sigma v is smaller than 1. This is, on this whole part, the green one, where you know that you have complete feature learning, the critical scale being just here, when you make equality here, sigma v equals 1. And in the meanwhile, in between this threshold of critical scale and the explosion scale, you have the lazy kernel regime with the NTK scaling that appears as the limit just here. So we already talked a lot about NTK scaling. I will come back to it later. So this is for the phase diagram. The phase diagram, just the right way of scaling the parameters, I mean right way according to the complete feature learning criterion, is this way. You have 4 criteria, you just apply them systematically, and in the end you can choose the scaling of all the parameters of the neural nets. Once you have identified this complete feature learning, you can move to the large width asymptotics, so this part that I'm now going to detail. So if anything is unclear, don't hesitate to slow me down. So I'm going to skip this one, and I move directly to the limit dynamics in the feature learning regime that we have already identified. So I'm going to consider an architecture that is slightly more general than the one that I showed at the beginning of my presentation, because now I say that the output f is a function phi of the input x and some z. And the z can give us several information. So as an example here, if I take vzx given this way for z being the gathering of u and v that I had previously, then I recover the 2LP architecture that I showed previously. But the choice of a more general phi this way allows me for considering slightly more general architecture. For instance, here I could consider a multi-head attention mechanism if I want something a bit more general than 2LPs. Then the gradient descent algorithm that I presented at the beginning in this slightly more general setting rewrites this way. So I initialize all my parameters z from the same law with independent initializations. And the scale now of this initialization law is over the 1. Because I have justified y in compute feature learning regime, I have to choose the initialization over the 1 here. And then I perform the gradient descent algorithm with a learning rate that has been adjusted according to the criteria that I just mentioned. And the question now is what happens as m goes to infinity. As m goes to infinity, if you look at this sum intuitively, if you assume that you have a bit of independence, I mean sufficiently many independence so that a law of large numbers can be applied, then you can guess that as m is going to infinity, this quantity f of theta is going to converge towards an expectations over all the parameters z that do appear in the sum. And this is indeed what happens. This is going to converge towards an expectation of phi over the expectation being taken over some random variable z that accounts for the typical law of 1 parameters. In the large width limits, you don't need to keep track of all the parameters, but only the typical law is important, and the output is computed by taking an expectation over this. The only thing that matters is how does this law involve with time, since you are not concerned about the evolution of each parameters, but the overall law of the parameters. And the evolution can be obtained by just taking this and sending m to infinity within it. You see that the typical evolution of this z is going to be this way. So it's just the gradient descent that I already had hit that I take it for 1 single parameter, and this equation is the equation of 1 typical parameter as m goes to infinity. The difference being that now the output is computed by taking an expectation with respect to the law of this parameter and not by using many parameters. Only the law does matter. So the mathematical results behind this is the following one. You have a theorem. So I put an assumption here for simplicity. I said that update of ZK and FK is bounded and globally Lipschitz. So update on ZK and FK, I did not define it, but you can read it here. Update of one parameter is a function of ZK and of FK. So this is a function that I call update of ZK and FK. So under these technical mathematical assumptions that this map is bounded and globally Lipschitz, then I have a convergence result for these two LP dynamics. The convergence result is the following one. Indeed, if I do the difference in between my limit dynamics, Fz here, and the F hat, which was the initial dynamics, and I do a maximum over the n data points of a training set, then I have a quantitative error bond, which reads this way. It's a bond which is obtained with high probability, meaning that for any small threshold delta, then with probability higher than 1 minus delta, I have this quantitative bond. In particular, in this bond, I can observe a rate of convergence, where I can see both D and M appear. So since I said this, I directly move to my third comment on this limit, which is this one. If I want this to go to 0, if I want this limit to hold, then I need M to be very bigger than D, which is what I was explaining just here. If I want this assumption of D smaller than Lm to be true, then I need to send first M to infinity and then D to infinity. Actually, I can do even better than this, because since the limit is quantitative, I can allow both parameters D and M to diverge simultaneously, provided that M is bigger than D. So this is something important. But still, if I want to move to the very deep case, this one is only depth 2, so it's only a toy model for what I'm going to show next. This is not realistic, because as I said, realistic scalings are more D proportional to M and L bigger than 1, at least on the figures that I showed at the beginning. So this is the first comment. Second important comment is that actually, if I consider the two LPKs, the update map that I wrote here is not exactly globally Lipschitz, because I have a U and V, and having a product of this way hinders my map from being globally Lipschitz. But still, the result can be fine-tuned, and you have the same bond, provided that you add an extra assumption on the right-hand side, which is the bond only holds as soon as the right-hand side is small enough. This is really a technical condition. It's just to say that this result can be extended a bit beyond the Lipschitz setting, because the globally Lipschitz setting is quite restrictive otherwise. As I said previously, this is the only thing that matters now that we have sent M to infinity is not the value of the parameters themselves, but the law of the parameters. So this is why, actually, you can write a closed form dynamics on the law of a parameter instead of a parameter. And this dynamics is well known to be a gradient flow equation if you use a setting of optimal transport. So it's a gradient flow in the Wasserstein space of probability measures, for those of you who are familiar with this notion. And this has been well studied in all these articles and many other ones. And once again, I apologize if I forget to cite some of you. Another interesting question for the limit dynamics, especially once you have rephrased it as a Wasserstein gradient flow, is can you analyze its long time convergence? So what happens in long time when you do the training of the dynamics? And there is a very recent result that I want to advertise here, which is the local convergence of the limit, which was quite a challenge for a long time, and which was obtained by Lineix Chiza, Roberto Colombo, Maria Colombo. It's not the same family, important point, and Xavier Fernandez-Rial. Okay? Sorry?
Could you define what you mean by local convergence?
Local convergence. This means that if you take a global minimizer of the loss and you initialize close enough to it, you can prove a local Poiliak-Lojasiewicz condition that ensures exponential convergence. But it was quite a challenge to prove PL inequalities in this setting, and this is a question that they recently settled. Okay, so this is the theorem I wanted to talk about for the convergence of two-layer neural networks. And since I'm in a tutorial, I'm going to show a glimpse of the proof of it, just to give you the idea of how this works and how you can efficiently get quantitative convergence rates of this kind. And to make the demonstration simpler, I just assumed the update of zk and fk to be a bounded Lipschitz function, because for technical reasons, it's going to help. So I move to the sketch of proof. The idea is just I'm going to take copies. I'm going to take the initial system with the m weights, and I'm going to take m copies of the limit with the same initialization. The m copies of the limit are independent from one another because they are closed form dynamics on the law itself, self-consistency dynamics. But still, to make the proof quantitative, I'm going to consider m copies of them so that I can do an efficient coupling in between the m independent limit variables and the true weights of the finite M neural network. Once after doing this, the quantity that I want to bound is the difference in between the weights of a true ResNet at time k, of a two-layer network at time k, and the related copy that I have coupled by the same initialization. This is the quantity that I want to bound. If I take the evolution equation of each of these quantities, so this evolution equation for the limit, this is for the finite M network, and this evolution equation, I just take these two equations and I subtract them from one another. Because I made the assumption that the update maps that do appear here are bounded and globally Lipschitz, I have a control of this type. I have a constant time delta k plus the error that is made on the update map. So the update map was a function of x and fk. X is the same for both dynamics. It is the same input. So the only difference is about fk. I have to control this difference in order to close a discrete Grunwald argument on this quantity to get my final bound. So the whole question is, how do you control this difference? So the f hat at time k of the input, which is the output of a true neural network of width m, finite width m, is exactly this quantity. This is this. Similarly, the limit output is this one, fk, which appears here, because I said that as m goes to infinity, this quantity is replaced by an expectation over the law of the parameters. So the 1 over m sum over the parameters is replaced by an expectation. And the trick to control well this difference is to introduce this quantity, which is a hybrid quantity, in the sense that it's still a sum over m term, but now what I put here is the limit process, zg here, which are independent copies from one another. So the point of doing so is that now here I had a sum of m correlated terms, and now the sum that I have here is the sum of m independent terms. So I have split the problem into two smaller problems, one which is controlling this difference, but since I assumed that my map phi is Lipschitz, when I take this difference, it's just z hat minus z that appears, so that in the end this enters the delta k here. This is the delta k contribution that I get here. And the second term is just how you can control the concentration of a sum of m independent variables towards its mean. And this is a standard result from concentration theory, which can be handled using Hövding's inequality, plus a union bound because you want to take the maximum over the n data points, and this is how you get this. So this is just a Gaussian concentration inequality. And then once you've controlled this by saying that it's order of magnitude square root of d over m, and this is just the first time is controlled by delta k, you just have a standard Grunwald lemma that you can close, and you get the conclusion of a theorem. Is this proof argument roughly clear? So this is the standard method from mean field theory that we use here. We just use as a pivot in the triangle inequality the sum of m independent terms that are obtained by taking m copies on the limit that you combine with the concentration argument here to have a bound with high probability. Yes?
So are the z's under in the first line, not the z hats, they're IID, but are they following the mean field measure?
Exactly. They are IID copies on the mean field limit, but initialized with the same initialization as the true weights.
Okay.
This is how you get this proof.
So the first line's kind of about non-interacting versus interacting, and the second line is about concentration.
The first line, yeah, it's just about the fact that you
In
interact.
the F minus.
Here.
Yeah.
Yeah, exactly. This one is handling the interaction by putting it recursively in the grammar argument, whereas the second is pure concentration. Exactly. Any other question? Yes?
How are you interpreting which probability more than equal to 1 minus del? So is that where is that coming from?
This. Actually, if you take the concentration, the Hubble concentration inequality just for Gaussian variables, it's exactly what the Gaussian tails give you. The Gaussian tails. This is exactly the term of the Gaussian. The thing is, I initialized everything using Gaussian variables so that I can propagate sub-Gaussianity, and this is how this pops out. This is just the Gaussian concentration. Yes?
So can I ask maybe it's a silly question. Why is the ratio of D over M constant? Because is it the way that's how your Z's are being sampled?
The M part is once again about the Gaussian concentration inequality. And the D is just what happens when you keep track of a dimension when you do the quantitative Gaussian concentration inequality. Because the Z here are variables of dimension D. And this is why if you explicitly compute a Gaussian just to get the same rate, you're going to see that the dependence on the dimension is exactly this. So this D is just what appears in the Hubble inequality if you quantitatively keep track of a dimension in the Gaussian concentration. No more question? Okay. So I can now give just a few words about the regime I didn't talk about, which is the neural tangent kernel. So Mufan already told a lot about it, so thank you for that. And just in this setting, to motivate how the NTK regime does appear, it's just if you look directly at the evolution of a predictor of F itself, instead of looking at the weights. If you look at F itself, you have this that pops away from the gradient flow dynamics, and you can see that everything is controlled by this kernel, which is the empirical neural tangent kernel. And the whole question is, what happens to this kernel as M is going to infinity? So once again, you have the sum of M terms divided by M, so you would expect a law of large numbers type behavior in the sense that you expect this kernel to converge towards an expectation of something. But in most of the time, since the thing that is within the kernel does depend on the time t, the kernel that you will obtain as M goes to infinity will depend on the time. So it's not a closed form dynamics. However, if you do a specific choice of scaling, mainly you assume that the sigma v is very big compared to 1, sigma v being, in the 2LP case, the standard deviation of the initialization of the v weights, the v weights being the one that is outside the activation, just in front of it. Then you have something interesting that appears. Because sigma v is very big compared to 1, the learning rate staying over the 1, you can see that the initialization is way bigger than the updates. So that in this asymptotics, you can say that the evolution of Vg is little o of 1 as M goes to infinity. So because you have a huge initialization and a small learning rate compared to it, it's exactly like if the V weights were not evolving. But because there was the complete feature learning condition, not the complete feature learning condition, because this one does not hold in the ATK regime, but because of this other condition, which is the balanced lost decay, so the one before feature learning that I introduced, you have that eta u, so the learning rate of the u weights, the one which was inside the activation, should be proportional for having a balanced loss decay to 1 over sigma of v. So if sigma of v goes to infinity, this learning rate goes to 0. Meaning that if sigma of v goes to infinity, then the learning rate of the u weights also goes to 0, meaning that the pre-activations do not evolve also in the asymptotic. So in the end, in this regime, you can see that the pre-activations do not evolve, the V do not evolve, meaning that this kernel is going to stay concentrated on its initial value. So as m goes to infinity, this is how you have the neural tangent kernel that appears, and in this specific regime, you can observe a closed form dynamics in the predictor. Just to give the idea of why this choice of scaling does condition the other ones. This is interesting to say that if you just relax the complete feature learning criterion, the last one, because of all the other ones, only assuming this to be big is sufficient for making the evolution of both the V and the U stationary. So all these criteria is very intertwined to one another. And the only thing that made the difference in between this regime and the previous one was the fact that I wanted the complete feature learning, the local updates to stay over the one. So I reached the end of this first part. I presented 4 criteria in order to scale a neural network. First, the non-explosion criterion, quite important. The second, feature diversity at initializations, which was already important to choose the scaling of initializations. Then the balance loss decay, the one that I just showed, and what was in particular conditioning the choice of the learning rates given the other parameters. And the last one that identified the complete feature learning regime, which was maximum local update. For 2LP, I showed a first mathematical result, which is the infinite width limit. This is a now well-known result, which holds that rate big O of square root of D over M. And in particular, you have many other descriptions of this regime using a mean equation or Wasserstein gradient flow if you are in the optimal transport setting. And one important point, since today I said that I stay in this regime, this limit towards the asymptotic that I described only holds if this ratio goes to 0. Because if you take this ratio going to infinity, then it's a totally different question, which was raised also by Blake in his talk. This is the end of my first part. The next part being the high-dimensional version of this. So after doing m goes to infinity, I would like to show how we extend the dimension to infinity afterwards. How much time do you have? 55 today, okay. Anyway, I will continue after lunch, so you won't be saved. Yes?
So for the first part, did you just assume that n is finite for everything?
Yeah, my number of data is always finite. It won't change. And I mean, it's not realistic at all. I acknowledge this, if you want to read to understand the learning of it. But my point today will be only about the architecture and the scaling of the architecture. So n will be always finite. And from now on, most of the time, I will even consider n being equals to 1 for simplicity, because since it's finite, it doesn't really count. Any other question? Yes?
Maybe it's a silly question. If I understand correctly, I think we're choosing the scaling specifically to avoid the lazy regime. But why in the end, because we take the learning rate to be the minimum of 1 over sigma b squared. Why again? Because learning rate becomes so small, we again back in the lazy regime. Am I missing something?
Because I have imposed this balance loss decay criterion, I could still learn in other situations, but if I want to respect this balance decay criterion, which seems reasonable for some intuitive reason, you want the update of the loss to stay over the 1 as you send everything to infinity, then sending sigma v to infinity forces the NTK regime. But here you have no SDA regime. No SDA regime because you have only depth 2, which won't be the case when I will take L bigger. For deep neural networks, the phase diagram will be slightly more complicated with other regimes appearing.
So is that like a negative result for two-layer perceptron?
Yes, this was quantitative. So, and this result covers all the asymptotics where D is smaller than M. Smaller than M because this is how this criteria does specifies to the 2 LPKs. But for now, I only showed what happens for fixed D and M goes to infinity. Now that M is infinity, I'm going to show what happens for D. Okay, so to be able to send D to infinity, I have to slightly adapt my setting. Because I'm going to take input X that lives in a finite dimensional space. So this is the first restriction that I do. I consider that the dimension of the input here is fixed. And the dimension that is going to grow to infinity is the dimension of the embedding itself. So first, I must take my input data and embed it in a bigger space. To do so, I use an embedding matrix here, which is called W in, and enter the ResNet. I mean, the 12P. ResNet will come later. So I define this H0, which is only something that depends on the data and nothing else, which is the embedding of the data using my embedding matrix. In realistic models, you have to train also the embedding matrix for it to perform well. But for my presentation today, I will consider the embedding and unembedding matrices to be fixed, given. So that I just focus on what happened with respect to the embedding dimension. So once I have embedded my data X in a d-dimensional space, I do exactly the same as previously. I consider my 2LP defined this way with some weights V, but now the V is no more scalar. The V is a d-dimensional vector because I want all the computations of my neural network to hold in a d-dimensional space. And afterwards, in the end, the output H, or H1, sorry for this typo, I just take it and I unembed it. I plug it using an unembedding matrix W in the output space, whose dimension is also fixed. So here I must add, if I have some place, the output dimension, both of these being fixed. The only thing that's going to go to infinity is the width and the embedding dimension. Okay, one other important thing to mention here is what appears in the pre-activation. So in the pre-activations, previously I had a dot product of the input, which is now the embedded input, and the first parameter, u. But since now everything is d-dimensional, I have to rescale stuff so that this makes sense. This is where this notation 2-bar comes at play. So I define the 2-bar notation. The 2-bar notation is just the normalized scalar product in RD. So it's just 1 over d, the sum over the d coordinate of the product of coordinates, this way. So this is a notation that will appear throughout my presentation, so I just keep it here. If you have a doubt, this is here. And once again, this 1 over d is motivated by the fact that I want stuff to stay over the 1 as I will send dimension to infinity. But once again, at this stage, this is a mere convention because I never specified how I scale my parameters with respect to the dimension. So my choice of scaling will be affected by the fact that I put this d from the very beginning. But I anticipated the shape of the limit equation. This is why I put this d from now on. And similarly, this 1 over d here plays the same role. It's just to encode an embedding in a pleasant way as d goes to infinity. But since for now I have not specified the scaling of this matrix of unembedding, this 1 over d is totally arbitrary. Now I'm going to specify these scalings. So as previously, I have initialization parameters. I initialize my u and my g using independent initialization, Gaussian 1, with standard deviation sigma u and sigma v as previously. For the sake of simplicity, I said that I considered fixed embedding and unembedding matrices and that I do not train them. Actually, the training of embedding and embedding can be incorporated in this, so this is not a true restriction. But for the sake of simplicity for my presentation, I consider this given and being Gaussian this way. So the day in and the day out, once again, are fixed input and output dimensions. And I have additional choice of scaling to be made, which is the scaling sigma en and sigma out for the standard deviations of embedding and unembedding. And the question is the same. Now, how can I send everything to infinity? So first, I have to play the same game, which is choosing the right scaling, but now with respect to the dimension, because previously I wasn't accounting for it. Then, once my scaling are chosen, I have to send the width to infinity. And then I will move to the part that interests me in this second section, which is how to send D to infinity. So I'm going to quickly follow the same steps as previously, which is just a nice way to check whether or not it's clear for you. Do not hesitate to interrupt if it's not the case. So this is exactly the same game. I define the pre-activations, the activations, and then I play with all the criterion one after another. First criterion, non-explosion. So the H was defined this way. So it's just the embedding of the data. So the H0 was defined this way, sorry, this is H0. And then I compute the H from the activation, which at the initialization are using the embedded data, W in time X. So the first criterion is I want the output, but now not the real output of the system, the output in embedding space to stay over the one as everything goes to infinity. So this, once again, the same computation as previously, using the same computations, tells me that the standard deviation of sigma v, the weight which is in front the activation, has to stand over the square root of m. And something important, which is what I just said, which is I said that I want everything to stay over the one within the embedding space. This is a choice, actually. This is not something that is needed by the neural network. Why? Because the true output of a neural network is the F, so the unembedded data. But still, what happens within the embedding, I can scale it wherever I want. Because if I just say that within the embedding everything diverges, I can just rescale the unembedding matrix so that it doesn't diverge. So in the end, the only thing that matters is the output. The output has to stay over the one. And the question of how I scale things within the embedding is at the beginning a convention. And once I have fixed this convention, everything will be imposed. So this first choice of convention, the fact that I want everything to stay of order one within the embedding, dictates that, in particular, this quantity stays over the one. And this is why the embedding has order of magnitude 1. But once this is fixed, then it has been decided forever that within the embedding I stay over the 1. And this is why the second computation does make sense. I want, thank you, this to stay over the 1. So this is the reason why this sigma v has to stay of this order of magnitude. And similarly, for the unembedding, recalling that for convenience, I had put this 1 over d factor in the definition of an unembedding. This is why the standard deviation of the unembedding is square root of d. But once again, these two things are just big O. So the order of magnitude is not totally imposed. And this is why I will have a degree of freedom later on while doing the phase diagram. The second thing, feature diversity at initialization, exactly as previously. And the same reasoning does apply, but now when I do the computation of the variance, I have to take into account a sum of d term, and this is why the sigma u here has to stay of order square root of d. Previously, it was just of order 1, because the dimension d was fixed. But this is telling me that the right choice for feature diversity at initialization is sigma u, which is not a big O of square root of d, because I really want this thing to be over the 1 from the very initialization. This is exactly a theta of square root of d. So this fixes the order of magnitude of sigma u. And for other quantities, I play the same game. So once again, I did an arbitrary choice by putting D and M here in my gradient dynamics. This choice is not a true one because at this stage I haven't made precise how I chose the learning rates eta v and eta u. So I just compute the update equation this way. From these update equations, I can compute the pre-activation. Then from the pre-activation, I compute the evolution of the output f theta at time t. From this, I compute the evolution of the loss. And after having computed the evolution of the loss, I play the same game as previously. I got two terms. The first term is of order eta v, because it's m term balanced by m. And my previous conventions did impose that this quantity stay over the 1, because this had been imposed. And now I have to play with this second term. So the main difference in between this second term and what we had previously is the fact that now we have this quantity that pops out. So this quantity, which is the normalized scalar product through this definition of the n-embedding matrix and the weights V. And since I'm looking at what happens close to initializations, I can assume, because at the initialization I had independent initialization, that these quantities are independent from one another. And since I have a sum of centered independent terms renormalized by D, this is why I get an extra D dependence here in the scaling. So this is exactly the same computation as previously, but now I made explicit the dependence on the embedding dimension D. And since I have the same computation, I can draw the same conclusion with this additional D factor, which is the fact that if I want everything to stay balanced, this quantity has to stay over the 1, this quantity has to satisfy this, because if you observe this, this was implicitly here, eta u, eta v square. And this eta u has to satisfy this order of magnitude. So if I take eta v over the 1, I can say that eta u is also over the 1, and I exactly recover my previous criterion, the one that I had previously, that eta u was the minimum in between 1 and 1 over the square of sigma v. But I have an additional D factor that pops out from the fact that I kept track of a dimension from the computation. This is how I obtain this conclusion. So the feature learning thing now is telling me that I want the evolution of the preactivation to stay over the 1. This is how I can identify this last regime that tells me that eta u and eta v has to stay over the 1, and then the initialization of the weight sigma v is a big O of, it's a big O of square root of D. To be in the feature learning regime, it should even be a theta of square root of D. Sorry for this. Because the fact that it was a big O of square root of D, we had it from the non-explosion criterion at the beginning. So there is a typo here, it should be a theta. So exactly as previously, by putting all together the 4 criteria plus adding the explicit dependence on the dimension, this leads to a new phase diagram where now the dimension has been taken into account. So this is the same as previously, meaning that if you are beyond the threshold that we obtain, which is 1 over square root of m, you have explosion of a neural net. In the meanwhile, you are in the lazy kernel regime. And before it, you are in the complete feature learning regime, where you have maximum local updates in addition to the local update of the global update of the loss that stay balanced over the 1. And the new critical scale that makes the difference in between these two regimes is now explicitly depending on the dimension D. This is exactly the same computation with the dimension D on the top of this. And now, as previously, I can send the width to infinity, now that everything has been properly rescaled. And then I will send the dimension to infinity this afternoon. Okay, so the limit equation is the same neural mean equation as previously, in the sense that instead of having a normalized sum of m terms, you have an expectation over the value of the parameters u and v. Now I stick to the 2LP regime. I do not consider the general phi, although it could be possible in some case. To make things simpler, I stick to n equal 1, what I had written here, as I said that the behavior with respect to the number of data points is not my point today. And I get the evolution, the typical evolution of the update. So delta v here is directly, I should write it, the evolution, the increment of the weights with respect to initialization. And this is really important because I fixed the order of magnitude of the initialization, but not of the updates. The order of magnitude of the updates is determined by the learning rates themselves and the whole equations. So delta vk is just vk minus its initial value. It's just rewriting the gradient flow evolution. Okay. So at this stage, I get the same thing as previously. Previously, it was a z. Now z is the couple u and v. This is a random variables. The only thing I am interested in is the typical law of this random variable, as only the law is involved in what happens within the neural network. So in the neural mean equation, I'm just taking an expectation over the joint law of u and v being described by these equations. And because it's exactly the same setting as previously, just keeping track of a dimension explicitly, in this slightly different regime, but the proof works exactly the same way, I have the same result, which is with high probability. So for any delta, with probability bigger than 1 minus delta, I have this quantitative convergence at the rate that I previously showed. And now everything is ready in the sense that the scaling are here, including the dimension d. We have sent the width to infinity. We got the neural mean equation that we previously obtained, so we are ready to send the dimension d to infinity.
Does this imply that the function wouldn't converge in a proportional scaling? Like if d was...
I mean, this does not say that it won't converge, but it says that the limit won't be the same.
Limit won't be the same, okay.
Because this bond does not require anything, but
Yeah.
it's always true.
I would just imagine that there's, if you scaled d and m linearly,
Yeah.
my intuition would be that you'd still have a 1 over square root of d kind of,
If I take d proportional to m,
d proportional to m.
actually,
Space, so
you can have a result of this using the tensor program framework, for instance,
Okay.
d proportional to m, for L equal to E centers, but not using this method, because if you take d proportional to m, this bond is just irrelevant. This is true, but it's irrelevant. It doesn't give you convergence.
What, is that bound a different flavor, or like, what would you use for that?
For the tensor program thing,
Or for yeah, if you wanted to like do a similar kind of instruction.
actually,
Oh, it's okay. We can talk. Let's talk about it.
I mean, I would spoil on my next slides if I answer right now. So we may discuss this after a few slides. 1 minute. Okay, so my last minute is just to tease what I'm going to say this afternoon with the next slides. What's the main problem of sending d to infinity? The problem that we will tackle this afternoon, which is this quantity. This quantity is the neural mean equation, where I have the nonlinearity applied to the preactivation, and I said that I normalized this way the preactivation, and all my choice of scaling was done with respect to this. From the choice of scaling that I had, using this update decomposition here, I have roughly this happening, in the sense that my weight I time k, my v, is the sum of its update and its initial value. But because of the choice of learning rates that was imposed by the 4 criteria, this is over the 1. But the choice of initialization that was made at the very beginning to get feature learning at initialization makes the initialization being over the square root of d. So I introduced a new random variable v that stays over the 1, and I just made explicit the square root of the initialization dependence. And this is why this is getting tough, because this weight here has an update over the 1, but its initialization is huge. And contrary to previously, we are not in an ATK regime. So for the high-dimensional regime, we have to take this into account, the fact that using these notations, this weighted dot product reads this way, with the first term, which looks like a central limit theorem term. It's 1 over square root of d, because the 1 over d here has been balanced by these initializations, plus a second term that has the usual mean fit scaling of the law of large numbers. But the very difficulty of this is that you have to account for this central limit theorem in some way. And this is what I will explain this afternoon. So I stop here for now. Thank you.
So thank you for the great talk. Looking forward to much more. I think we have time for maybe one quick question, if any.
Very quick question. I mean, just so, usually the gradient descent update are like a continuous gradient time, right?
Mhm.
And you complain that you're dealing with this continuous process. Is that like, do you interpolate or something? Or?
This continuous process is in time, you mean?
Yeah.
Actually, all this is discrete in time. So the gradient updates are discrete in time.
Yeah,
The only moment I use continuous process was for designing the criteria.
oh, okay. So that's only for designing the
Yeah, this is the only time in my presentation where you could have the t variable, which was for designing the criteria, because I needed to look at the gradient descent algorithm in continuous time at its initializations. But since these criteria are a bit more hand-waving, they are not mathematical results. They are just heuristics that helps you from small computations choosing the scalings. But all the mathematical theorems that I show are with discrete gradient descent, with some discrete k.